Right, students, let us start with this. Okay, this topic is more theoretical. Let me continue now. See, petroleum, the word comes from petra, which is rock, and oleum as in oil. It has many other names: rock oil, mineral oil, or crude oil. These are all the names that have been formed. Okay, mostly it floats over the salt water, in seas and oceans, and it would be covered with atmosphere of gases, gaseous mixture, which is known as natural gas. Yes, students. The composition of petroleum, if you check out, essentially it will have mostly hydrocarbons. So if you check out the composition, it will have hydrocarbons. Okay. And hydrocarbons, if you see, we can have a straight chain, we can have a cyclic chain, we can have aromatic hydrocarbons. So most of them, if you check out what are the types of hydrocarbons, straight chain forms, that would vary from around 30 to 70%. And if you see cycloalkanes varies from 16 to 64%, depending upon the well, depending upon where is the location, you will get various type of hydrocarbons. Okay. And we can also get aromatic hydrocarbons, which is approximately 8 to 15%. Please remember, you don't need to mug up any of these percentages, just that you know the straight chain form of hydrocarbons are more. That's all you need to know. Okay. Now, there would be some amount of sulfur containing compounds in it. Correct. So some sulfur containing compounds, mainly mercaptants. These are called RSH, which are mercaptants. Okay, this is the form most of this will have. Okay, students, I hope you got an idea about what is petroleum, right? What is their composition? Next, if you see natural gas would be mostly above the petroleum deposits, correct? It would have mostly low molecular weight alkanes, especially methane and ethane. So composition wise, if you check out, it would have methane, which almost has 80%, and all of these are by weights, 80% by mass. Then ethane around 13%, and propane around 3%. In short, all of them would be low molecular mass compounds which will be present. Correct? In case, if we take this natural gas under high pressure, if these gases are being observed, or we can in fact compress these gases and convert into a cooking gas, which is what we call it as LPG. Correct? This is liquefied petroleum gas. Liquefied petroleum gas. Right? So I hope you got an idea about what is natural gas.
Sir, what is the meaning of under high pressure?
If we take natural gas under high pressure, it will convert into a liquid form, and that is what we use it as a fuel for cooking purpose. Correct? So under high pressure, most of the gas like propane and butane, the combination of this would be highly inflammable. Correct? And it produces a blue color flame, and that is what we use it, right? Okay, next. How does the petrol refining usually done? So if you see petroleum refining, correct, most of the petrol that has been found would be almost ranging around 500 to 15,000 feet deep inside the wells, or either in the sand areas or in the sea areas. That is where it is mostly found. And all of these gases which are present, natural gases, they are also under high pressure in those particular areas. And from there, when you extract petrol, right? So mixture of both petrol and gas will come out of it. Now, this petrol which is obtained would usually have a lot of impurities like sand, some amount of salt water, correct? Some sulfur. So this entire mixture which comes over, so mixture of liquids, sand, correct, and brine solution, which is salt water, correct, and some sulfur, which comes all together. This is what we call it as crude oil. Okay. Now, sand is slowly freed by mechanical separation. By using mechanical separation, sand can be separated out. Then, most of the crude oil is subject to fractional distillation. Right? Now, the process where this crude oil is separated into various fractions depending upon their boiling range. What are the boiling points of different impurities which we are heating? Right? Most of the crude oil in the fractional distillation is heated up to 400 degrees centigrade. Right? And it is introduced in the long towers. From there, it will start slowly condensing. Okay, and the ones which has low boiling point, like methane, ethane, they will be collected at the top of the column, and that is separated out. And slowly the rest of the form, which is mainly as a residue, correct? So that will be mostly wax, that is collected at the bottom. Okay. If you see the composition, mostly gases which are uncondensed gases, correct, would be mostly methane. Okay, uncondensed gases, as in it will mostly come in a gaseous form. We will take out from the tower and directly take it as a natural gas, C1 to C4. They will come as mostly uncondensed gases. Then we'll get something called crude naphtha, which is from C5 to C10. Got it? Whose boiling point is in the range of 30 to 150 degrees centigrade. This is the boiling point. Then comes kerosene. So there was one question once it has been asked, correct? So what is the range of kerosene? 25 to 30% kerosene can be obtained from here, which is of C11 to C16. Okay, coming around 150 to 250 degrees centigrade. And all the heavy oils, that includes diesel and more fuel oils, which we call it as heavy oil. Around 25 to 30% of that heavy oil, which is ranging between C16 to C18. This will come around 250 to 400 degrees centigrade. The rest will be all residue wax. I guess this point is clear, everyone, right? Now, if you see petroleum ether, so if you, when we check about crude naphtha, it would have petrol or gasoline or any form of benzene derivatives. Most important out of it, from crude naphtha, the important item which you will get is petrol or gasoline. So if you see petrol or gasoline, the range of petrol or gasoline here is around 30 to 70 degrees. This is the boiling range. And mostly it contains the composition of C6 to C8 carbons. For it, and you know where it is used. So it is used mostly as a motor fuel. This information you must know. Got it? Now same naphtha can also give some benzene derivatives. Benzene derivatives are mostly used as solvents, which is used for dry cleaning. Okay. Benzene derivatives from naphtha are used as dry cleaners or dry cleaning solvents. Yes, that is clear. See, the residual oil whose boiling range is more than 400 degrees, that would be lubricating oil, wax, Vaseline, okay, petroleum jelly, what we call it as, we also call it as pitch. These are all the forms. And what are they used in? They used in making candles, boot polish, got it? They we use in ointments, lubricants, paints. These are all the areas in which more than 400 degrees centigrade boiling point, if it was. Okay. Now, normally the purification for all of this, right? If you take petrol or diesel, or for that matter, any benzene derivatives, correct? Purification is done depending upon the demand. What exactly is the demand? Correct. Next, if you see one process, I'll just show you one of them. If you see purification depending upon different demands. One is treatment with H2SO4. When you treat that with H2SO4, got it? Mostly like gasoline, petrol, kerosene, okay, diesel. These are mixed with sulfuric acid to remove any aromatic compounds. Like if you have thiophene and any sulfur compounds, which will actually impart a offensive odor to gasoline, right? So we are trying to remove that and make them less corrosive. So let me put that as a point. On treatment with H2SO4, sulfuric acid removes aromatic compounds like thiophenes. Which imparts offensive odor. Okay, that's the use. Make a note, everyone. Yes. Not pleasant for the nose. Correct. Iron is carbon aromatic compounds are usually pleasant, but if it is sulfur aromatic compounds like thiophene, they are unpleasant. They'll have foul smell. LPG, like I said, it is called the liquid petroleum gas. It mainly consists of, this is the JE question once asked, what does LPG contains? It mainly consists of mixture of butane and isobutane. Okay. And a very small amount of propane is being added. Okay. Small amount of propane. Another JE question that was once asked, I mean, these are all very old JE questions, correct? These were not asked now. One more question that was asked is, you remember, I mean, when you switch on the gas, we will get a foul smell, right? Correct. That is to make sure, to detect any gas leakage happening. So the foul smelling gas added to detect, right? So to detect the gas leakage is mercaptan, ethyl mercaptan, which is C5H5SH. So this will have that foul smell. All right. Typically, Indian standards maintain 14 kg cylinders, in which we compress the petroleum gas and make it into LPG. Got it? And it would usually give a blue color flame. Okay, and its calorific value is approximately 50 kilojoules per grams. So it gives around 50 kilojoules per gram. One of the reasons why we use LPG is that it gives complete combustion of fuel, which includes butane and isobutane. So there is no other residue or half combustion that happens during the reaction here. Got it? So the combustion gets completed. Okay. Make a note, everyone. To increase the combustion, what do you say? Ignition rate. Got it? Propane ignites faster compared to butane. Incomplete combustion, propane, methane, ethane, correct? Because they are, gases which diffuses very fast. Okay, so they will come out very fast. So the amount of oxygen supply through that small pinhole which comes, that is not sufficient enough to completely make a combustion of those gases. Okay, petrol and gasoline, no beta, slightly different. They would have composition differences. Boiling point wise they are same, but they have composition differences. Petrol will mostly have isomers of heptane, got it, while gasoline will have more isomers of hexane, got it. Only composition differences. Next, CNG is compressed natural gas. Compressed natural gas. This contains mainly methane. Mainly methane. In fact, it could have 95% of methane. Okay. Clear? Now, because we are using in bigger containers and the amount of oxygen supplied in natural, outside on roads, it will be easier to catch up with more amount of oxygen. So here it might give a complete combustion, right? If the engine is bigger in size, which is what we do it in running buses, correct? So CNG is a better fuel. This is also a compressed natural gas, right? And slightly better in terms of using it at a high quantities. Everybody clear on that? Now, if you see what is the other 5%, right? So the rest of the 5% is made up of ethane, propane, and butane. But mostly the combustion happens with methane. Got it? Yes, if you compare the CNG, because it has methane only, the side products would be less. So it is used as a better fuel so that it releases less amount of carbon dioxide. Most of this will completely turn into, if you compare to that of a regular petrol or diesel, this would have a complete combustion, right? And used as a better fuel for running buses, cars, and so on. Most of the autos and commercial vehicles that used in the cities are run by CNG now. Okay. Next, if you see when it comes to the methods of manufacturing petrol or gasoline, right? Methods of manufacturing petrol or gasoline. How do we do that? First, we can do it by cracking. Okay. Basically, cracking is that process in which high boiling fractions containing hydrocarbons are strongly heated so that they will convert into smaller hydrocarbons. Okay. For example, if I take decane, right, like I take CH3, CH2, 8, CH3. This decane, when it cracks at around 500 degrees centigrade, so basically you heat to such level of temperature, then we might get different combinations. We might get an octane, we might get CH3, CH2, 6 CH3 plus an alkene, CH2, C2H4. So octane and an ethene, or heptane and an propene, hexane and butene, pentane and pentene, butane, hexene. Like that, we can get different combinations. Okay. So slowly it is being cracked into smaller hydrocarbons. Got it? So these type of decane type of molecules, which may not be, appeared directly as a natural source. So these can be synthesized, and from there they will be cracked into manufacturing petrol or diesel. Yes, friends, that's how the cracking is done. Okay, so whenever we do cracking, hydrogen gas is released. Got it? Understood? Because at high temperature, so hydrogen gas will release. So one part of that would become alkene. Clear, beta? So overall reaction is this, that any higher alkanes in the range of 400 to 800 degrees centigrade on heating, you will get an alkane, an alkene, and an H2. It's very high. It's around 87, I guess, 87 kilojoules per gram. Not required for your exam, don't worry. Okay. One way of getting isooctane, because isooctane is something which will be useful for it. This can be done when you take, let me write down that. If we take petrol, which is obtained by polymerization of simple hydrocarbons. During cracking. Correct. Now, petrol is also obtained by simple polymerization. Polymerization of simple hydrocarbons here. Correct. And this polymerization is done in the catalyst like H2SO4 and H3PO4. Now, such type of reaction can be asked in exam. Like we have CH3, C double bond CH2, and that when you treat with another mole of it, CH3, CH3 double bond CH2 with 70% H2SO4. Basically, I'm taking 2 moles of this 2-methyl propene. So these 2 moles of 2-methyl propene are undergoing polymerization. So what do we get here? We'll get CH, one more CH3 comes here, and CH2, C double bond, CH2 and CH3. Okay, so finally a new alkene would come here. From there, we add H2, we do hydrogenation to get the molecule this way. CH3, CH2, CH, CH3 and CH3. This molecule, what we got is isooctane. Remember the structure of isooctane, very important. Not too big, it should be useful as a fuel. So you can make it into the form of a petrol, gasoline, right? Correct. So these type of alkenes are used.
The mechanism is not important.
Not now. When you do it in the alkene part, you will learn it. Okay. This is an addition reaction. Basically, first a double bond will get added with proton. It will get to form carbocation. On that carbocation, again this pi bond attacks, you will get this. Okay. So not very difficult also, but as of now not needed. Okay. My main objective is to make sure you memorize isooctane. It has a very important use going ahead. So I want you to memorize that. Ask mom. Sorry. Right? Everyone, check out isooctane carefully. It has 1, 2, 3, 4, 5. 5 carbon main chain. And this second carbon will have 2 methyl, fourth carbon will have 1 methyl group. This is how the isooctane. Now, when it comes to synthesis of petrol, correct? This can be done in 2 ways. One is a Burgess process, the other one is a Fischer-Tropsch process. Honestly, this is an engineering course. Okay, we have it in the, when I was in IT, it was in my second year first term. So synthesis of petrol by 2 methods. First, Burgess process, which is the hydrogenation of coal. So if I take coal and hydrogenate that in the presence of Fe2O3 at around 400 to 500 degrees centigrade, 250 ATM, it will give mixture of hydrocarbons or crude oil. Correct? This is called synthetic petrol. Okay. This much detail is enough. Otherwise, synthetic petrol, this is a huge topic, Burgess process, how it goes. JEE level, this is how much you need to know. How the coal is being treated with H2 and what do we get. right? Second, this is Fischer-Tropsch process. So in this method, what we take coke. Okay, coke is nothing but a black fine powder of carbon that we treat with steam at around 1200 degrees centigrade. On doing that, we'll get water gas. CO plus H2 is water gas. Got it? And this water gas in different compositions, like CO plus H2, in various compositions, if you treat with cobalt or nickel and heat it, we'll get mixture of hydrocarbons. So this is a better process if you compare both processes, Burgess and Fischer-Tropsch. Fischer-Tropsch is a better process to synthesize petrol. Knocking is nothing but that metallic or rattling sound that comes when when any of the fuel engine is on. As soon as you kick the engine, or any of the engine or ignite an engine, you suddenly see a metallic sound that comes. So metallic sound produced due to irregular burning of fuel is called knocking. So we will use certain anti-knocking agents to reduce this. Got it? Now, if you just apply the Carnot cycle, you may be learning it right now, correct? So you may have seen the fuel efficiency. So fuel efficiency can be increased, right, if you reduce the knocking, because most of this sound, most of the energy is lost in the form of sound. So if you minimize the knocking, it would become a better fuel. You'll see all that servo 40, right? So those kind of lubricants which are also used. So along with that, there are certain things which are added to the petrol. All will try to reduce this knocking property. Okay. Now, when it comes to knocking, in general, if you consider knocking, straight chain alkanes will usually produce more knocking than the branch chain alkanes, as compared to that of olefins as in double bond containing compounds, then cycloalkanes, then aromatic hydrocarbons. Better remember this order, how it is, okay? So what we do whenever we use a fuel, first we'll try to compare which kind of a alkane will give the least amount of knocking and which will give most amount of knocking. So to measure that, we have scaled it into two parts. Heptane was found to give the maximum amount of knocking. Got it? So that is given something called as an octane number, which is a relative measure of knocking. And the octane number given for heptane is 0. While isooctane, just now we have learned the structure. Isooctane has an octane number as 100. So 0 represents maximum knocking, while 100 represents minimum knocking. So we want to ensure somewhere in between these two and more close towards this octane number, the fuel should be. So which will produce less amount of knocking. Correct. So think this way, octane number of any sample may be defined as percentage by volume of isooctane present in the mixture. Octane number is percentage by volume of isooctane present in a mixture. Okay, present in a mixture of octane, isooctane, and heptane. Okay, and that has the same knocking performance as the fuel itself. Got it? So we will check out what is the percentage of isooctane to that of mixture of isooctane present in the mixture of isooctane and heptane. We will check out how much decibels of sound this will make, and accordingly compare what is the percentage amount of knocking it has. So for example, if you contain a best performing fuel, that would have around 60% of isooctane and 40% heptane. If you take these two, then whatever the sound that produces, correct, that is the least which has been observed in a mixture. Okay, so then we say that got it. So we can say this is a good amount of isooctane percent. So we say the fuel has octane number of 60. I guess you understood what it meant. Clear, everyone? This is example. No, every fuel has different knocking value, no beta. So you are measuring that with I'm saying every fuel has different type of knocking. I'm comparing that decibels with the different ratios of isooctane and heptane. Clear, beta? So if you am getting an percentage of 60 and 40, which means the fuel has an octane number of 60. Got it? What, beta? Yes, beta. If it is a reverse composition, octane number would be 40. Okay. Usually gasoline has 60 as the octane number. Yes, tell me. Correct, beta. We compare that theoretically, how much amount of energy that would release using a composition of 60% and 40%. If that matches with the fuel efficiency of what fuel you are taking, we say that it has the octane number 60. No, some or the other knocking will come. Can you get an Carnot engine of 100% efficiency? Any heat engine of 100% efficiency? No, right? Next, let us see what are the anti-knocking agents. Yeah. Better is the fuel. Yes, beta. Okay. If you see Formula 1, I'm not sure how many of you follow Formula 1. All the Formula 1 engines have, very low octane number. There, the power is more important. So that's why you will see when the Formula 1 engine is on, it gives such a huge amount of sound there. All right. Now you see, what are the anti-knocking agents? First one, which is most used in earlier days, is TEL, tetraethyl lead. Correct? Tetraethyl lead is considered to have very good octane number. What is its composition? This is tetraethyl lead. Okay. When you take a composition of 63%, ethylene bromide, right? 63% ethylene bromide, correct? And 26% of ethylene chloride. Please don't worry, you don't have to remember any of these percentages, correct? Sorry, 63% of TEL and 26% of ethylene bromide and 9% of ethylene chloride, correct? So when you take this composition, okay, so then that would act like a better knocking agent, anti-knocking agent. So point is here, why we are taking ethylene chloride or ethylene bromide? This kind of question could be asked. What is the use of using ethylene bromide and ethylene chloride? See, when you take tetraethyl lead, so whatever the lead that comes from it, we will try to react with CH2Br here and convert that into PbBr2 plus CH2 double bond CH2. Correct. Now this is a volatile halide, so this can come out. What happens if you see most of the petrol pumps, it would have written unleaded. Okay, in all the petrol pumps it is written unleaded. which means we are not using TEL as the knocking agent. That is what it meant. If you take any Bharat Petroleum, HP, all the petroleums, they will definitely have this heading on them, unleaded, which means we are not using TEL in it. What happens when you take ethyl tetraethyl lead? Okay, on heating, it will start giving the depositions of lead. So in the engine, lead will start getting stored, and it becomes difficult to remove that lead, and the efficiency of engine decreases. So what we do, we will add some percentage of ethylene bromide and ethylene chloride in this percentage, so that it will get a volatile form of lead, and it will come out of the engine. But another problem is this lead which comes is harmful in the air when you consume. Okay, so when we inhale, so this lead becomes very dangerous. So that's why it has been stopped to use tetraethyl lead now. Most of the engines are unleaded. Clear, everybody? Now, what are the other methods by which we can use the anti-knocking agents, or what are the other forms of anti-knocking agents? I'll just take the latest one, which is more useful. This is called the BTX, also known as aromatization. In industrial name, this is called platforming. Basically, it's a mixture of benzene, toluene, and xylene. So it is called as BTX. You may have seen a lot of advertisements coming as BTX technology, or BTX is used like that. Got it. So once you get this BTX, correct? So octane value of the mixture of this is very high. Got it? So in fact, the octane number of BTX is around 90. This will definitely improve the petrol. Clear, everybody? Another simple anti-knocking agent that is used here, is an addition of methanol and ethanol. Addition of methanol and ethanol also reduces knocking. We do not get into the reactions. This much is what you need to know. Just like octane number is more useful standard for understanding petrol and gasoline, C10 number is used for grading diesel oils. I hope all of you understood what is the anti-knocking agents. Mainly two, TEL and BTX. See now, next term is C10 number. C10 number is used for grading of diesel. Right? C10 is nothing but hexadecane. Right? Hexadecane, which we call it as C10. Okay, it is assigned as 100. Got it? While alpha methyl naphthalene is assigned 0. Right, based upon the same property. Here also we'll check out the mixture of both cetane and alpha cetane and alpha methyl naphthalene, and compare what is the best fuel, best efficiency of the diesel. Got it? Most of the diesel which we use, all the buses and lorries which they use, they would have around 75% cetane and 25% alpha methyl naphthalene composition kind. Is this clear, students? Only this much from C10 number, only these two terms are important. Rest all terms, that is not there for our syllabus. Got it? Any doubt here, students?
So here also more C10 number, more efficiency.
Yes, beta. Octane number is most used for petrol and gasoline, while C10 is used for diesel. Okay. So that's all from alkane syllabus. Okay, this is a very borderline syllabus. not generally there for JEE directly. Now, other than this, there are few miscellaneous reactions which you will come ahead, but since they give small amount of alkane or the preparation slightly as a side product as alkane, I'm trying to provide that here. So write it as miscellaneous reactions. Well, hydroboration reaction, is about taking an alkene. Keep walking with me, everybody. RCH double bond CH2, and that in the presence of B2H6 and tetrahydrofuran, or I can use any other ether solvent. And in that, what would happen? B2H6. See, idea is this: we take B2H6, add it to tetrahydrofuran. Tetrahydrofuran is this. When you add it, we will get this as BH3 plus BH3 minus and plus. So basically, we are generating an electrophile here. So we are generating an BH3 electrophile, and pi bond is a nucleophilic site. So this nucleophile will attack on BH3. So this pi will attack here, and it goes through this transition state CH2, where hydride is trying to attack simultaneously with the carbon. Boron is being attacked by this pi bond this way. This is the transition state through which it goes. So from here, you will get RCH2 and CH2BH2. Okay, so this hydrogen is the same as this hydrogen which we have added. So if you closely observe, the boron, the hydrogen which was present on boron is added onto the second carbon of the double bond. Correct? And the terminal carbon is the one which is adding towards boron. And now boron has again become an electrophile because it has an empty orbital again. So 2 more moles of that alkene will react with it. So 2 more alkenes, RCH double bond CH2. They will react to give RCH2 CH2 with boron. Similarly, I have CH2 CH2 and R, CH2 CH2 and R. So these are called trialkyl boron, trialkyl borane or boron. This is the product which is formed, or rather this is the intermediate after which the further reaction will take place. From here we will have multiple reactions, students. If you want to get alcohols, we have other reaction. If you get alkanes, we have other reactions. So the important point is to prepare trialkyl borane first. So how this trialkyl borane is useful? See that this is the first step in this reaction. The second step is about how we are using this RCH2 CH2, try of that with boron, and if you treat that with acetic acid CH3 COOH in the presence of in acidic medium, we will convert this into an alkane RCH2 CH3, and boron will become boric acid. Yes, sir. Got it? Clear, everyone? Okay. Next, suppose if the same reaction is being treated in the presence of AgNO3 and NaOH, right? So if we treat this with AgNO3 and NaOH, all of this trialkyl group that will get coupled. So you'll get 3 moles of RCH2 CH2 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 and R. This is the way it will get coupled. So 3 moles of coupled products will come. In the presence of AgNO3, coupling is happening. In the presence of acidic medium, which is acetic acid, you will get a simple alkane. These 2 reactions, I hope you understood why we are discussing now, because they are giving us an alkane reaction. The other day we learned about isomerism reaction. Isomerism reaction. You can directly heat in the presence of AlCl3. Suppose if I take N-butane, we can directly react in the presence of AlCl3 and heat. Or to facilitate better, we can add concentrated HCl and heat. The heating is around 200 degrees centigrade, 35 atm. Got it. On doing that, we will get this as CH3, CH, CH3 and CH3. So alkyl groups will get branched. So we'll get isobutane. So someone was asking me like whether we should use HCl or not. Yes, we can use HCl in it, and that will help for this reaction. One more reaction. This is also, a reaction which is normally learned during ketones. But anyways, because it is giving an alkane form, this is called insertion reaction. Okay. Now, when you take CH2N2, I guess you remember this is diazomethane. This is diazomethane. Diazomethane on heating or using light, it can immediately give an carbene and N2 gas will release. Same way, I can prepare the diazomethane using ketene. We have done this during intermediates. So the sunlight or heat, we can get CH2 and CO. Now, if you take any alkane like CH3, CH2, CH3, propane, and I treat that with this radical CH2, it will undergo insertion. Got it? And insertion usually happens at the carbon which is more reactive in terms of radical. So this radical, secondary radical, is more reactive. So you can see CH3, CH3 will be formed here. Okay, students, think this way. Again, these are all mechanisms not required for you. H, so think this is homolytic fission here, and CH2 dot is taking away this proton. So this will become now CH3 dot, and this will become C dot. It will get terminated. So here it is becoming CH3, CH dot, CH3, and this will become CH3 dot, and both will get terminated to get this product. This is called insertion reaction. Now, but if you take N-butane now, okay, if you take N-butane here, so, I can get this product like this, correct? Or I can get this product, which is N-pentane. Major product would be isobutane. Okay, students. So that's all. These are a few extra reactions. Oh, okay. One more reaction while I was writing. Okay, before I forget, I gave you one reaction as Franklin reaction, if you remember. Franklin reaction. Someone pointed that out to me. Rx plus Zn plus XR. This in the presence of ethers. This is Franklin reaction. So we'll get R and R. Coupling reaction. I gave you that. I think instead of ether, that was felt. I think I made a mistake of writing ethanol, I guess. Just please make sure you correct that. Franklin is a reaction just similar to that of Wood's reaction. Same as Wood's reaction, okay? So these many reactions are sufficient, students. So you should be able to do well in this. Now, few of the reactions which I'll just summarize so that it's you're prepared for the exam. So we have learned any alkane RCH double bond CH2. If you treat that with H2 in the presence of nickel, palladium or platinum, it will undergo syn addition and it will give alkane. Reactivity, if you check out, always least substituted or the most reactive compared to that of more substitution, and so on. This is the first type of reaction you must remember. And if you know CAT and CSC, always remember these two. All right. So that makes it TAE and TST. Right, everyone? Second, if you take any alkyl halide, sorry. If you take any alkyl halide reaction with zinc CH3COOH or zinc concentrated HCl or zinc NaOH. In all of these cases, we will get RH. Alkane is the product. Third, red phosphorus HI, very important reagent. It can convert any form of alcohol, any form of write it this way, R CH2OH, R CHO, R COOH, or R CH2X halides. Any form can be converted into alkane, RCH3. Important. Red phosphorus and HI. What beta? Red phosphorus H, I don't remember better. Next, Wood's reaction, all of you must be aware of it. Rx plus sodium plus XR in the presence of ether will convert into R and R. So this is Wood's reaction. We have learned about two other reduction reactions, Clemenson's reduction and Wolff-Kishner reduction. Suppose if you have any C double bond O plus 4 nascent hydrogens, I'm just writing it as an overall reaction, you know the mechanism. That zinc amalgam, zinc HCl will give you CH2. Correct? Okay, in this, one of the examples that somebody pointed out me on WhatsApp, suppose if you have this way and I have OH, then what happens if at all I use ZnHC and concentrated HCl? First of all, this will get reduced. This keto form will get reduced, and here it will get protonated, and this will be relieved to get halides. But halides can also be converted. I think this step can also be done because we are using zinc and concentrated HCl only, right? Ultimately, we are using zinc and concentrated HCl, so which will provide sufficient electrons to get this. So the final product, make sure you write it. This alkyl halide will also get converted into this alkane. Okay, someone was pointing. No, not with this. In Wolff-Kishner reduction, it will happen. Okay. So I'm writing the next one. See, same reaction, I'll write it in Wolff-Kishner form. This, if you treat with Wolff-Kishner reduction, what is Wolff-Kishner? NH2, NH2, hydrazine in the presence of alcoholic KOH. So that will give this alkane. Suppose the same question was asked here, where instead of alcohol, I have halide. So the upper part will get anyway reduced. Now, depending upon the position of chlorine, secondary position is favored for both substitution and elimination. So both would happen, which means OH minus from the solution can replace this chlorine by SN2. This is by SN2 mechanism to give OH here, or we can get this OH minus can act as a base and extract proton to give an alkene. So we'll get mixture of these two. If it is at the tertiary position, only E2 will come, SN2 won't come. Yes, all of you understood that, right? Yeah, another very important reaction is Corey-Howe synthesis. Okay, so if you take 2 moles of RLi and treat that with cuprous iodide, chloride or bromide, it will convert into Li2, no, LiR2Cu. Right. This is lithium dialkyl cuprate. Lithium dialkyl cuprate. This, if you treat with any R-X, will form R and R coupled product. But very important point is this has to be, methyl 1 degree or maximum 2 degree. 3 degree will go for elimination because it will drive through SN2 mechanism.